is we're going to be talking about a lot of different things today, and I'd like everybody to listen first, because we're going to say some things that may go against some of what you feel, some of what you have experienced firsthand in your body, flying stuff like this. And so before you go raising your hand and saying, hey, look, I felt something different, let's go through the whole thing. Let us go through the entire process here and talk about it. And then we could talk about the differences between physics of what's going on in the whole system and what a pilot feels. Because what happens and how you feel in the seat of your pants and what you experience as the person hanging underneath the wing may not always be what the whole system is experiencing, right? So kind of hold those questions and let's talk about that stuff at the end. Because some of the things I'm going to say, until we get through it all, I think we will do a pretty good job of explaining at the end. Some of it builds on itself, and you'll catch it later on if you keep listening. So normally this is set up. I've given this a couple times now, and normally this is set up to I'm giving it solo, but this, thank goodness, I actually have Kevin this time. This is really good. A lot of what we've done here and a lot of the stuff that I've put together here hasn't been done in a vacuum. It's been done with Kevin's help, and he's the guy I call when I'm like banging my head on something and go, hey, I got to run a crazy idea past you. And we talk through it all. And so in large part where you may hear I and me, it's actually a we. And so just know that. And I don't have his stuff up, but I'm going to start talking a little bit about Kevin's background, and then I'll let him go, and then I'll tell you about my background, and then we'll start in on the presentation. But I met Kevin quite a while ago, and he was working as a paraglider instructor. I didn't actually take my training from him, but my friend did, and I sat in on it. And first thing I thought was, wow, what a good teacher. Clearly knows his stuff. And over beers, over the next few years, we kind of dug into aerodynamics and started talking our way through a lot of this stuff. Kevin's a pilot. He'd been to school for aviation. Worked as a paragliding instructor for 20 years, almost 15, 20 years.
Yeah.
Little known fact, he was probably the first guy in the U.S. doing any real acro paragliding. So the first person in the U.S. to ever do a SAT back in the day. So he was out tinkering with that stuff and sewing wings together and doing real world top of the hill aerodynamics testing on his own while he was working and flying stuff out at the hill every single day. So that's Kev. Anything you want to add, Kev?
I guess nothing specific. Yeah, I did a lot of instruction. I was USPA Instructor of the Year in 2009. That was a year after, Scott learned how to fly paragliders. And then, of course, Scott and I started working on testing together. But that was, as you were saying, just cutting stuff apart. I also have done beta testing before we started Fluid. I did some testing for, prominent paragliding companies and speed wings, and also helped out with some wingsuit companies as well, too, with some of their R&D and stuff for the past as well. So I've got a background in not only paragliding, but also just kind of just playing around with stuff and designing and making things work. So there you go.
So yeah, so this is a we. It's usually me. I don't spend as much time. I didn't get the slide added in last night, so my apologies. All right, my background is I've been paragliding for about 15 years, skydiving for about 26. I'm a pilot with a bunch of hours. Got a bachelor's and master's in engineering. I practice in a bunch of different states. I still practice. We design the parachutes and paragliders, so I do the numerical stuff. I'm the numbers guy, and Kevin is the hands-on guy, where I'm like, hey, look, I got an idea. The numbers say this. What do you think? How do you think we roll it into reality? At this point, we've done over 20 different models between parachutes, speed wings, and paragliders. Some of them never got released, but we've done a lot. We were jumping with seated harnesses back in 2009, both Kevin and I. We weren't doing it for skydiving. We kind of had another project we were working on. So we developed one and started jumping it to do something else. So well, that's kind of how we got our feet wet in this stuff. And next thing you know, we're building parachutes and paragliders. I've done a ton of extensive CFD modeling, correlated them CFD for seated and upright harnesses. So we do both. And we both fly high performance wings, foot launch, out of airplanes. We're flying this stuff daily. Like this isn't not some guy sitting in an ivory tower. So yeah, we're doing it. We don't do anything we're not asking you guys to do. Let's talk about it. Everybody calls them supine harnesses, right? If you look up supine in a medical book, they usually talk about someone laying down. No one's laying down in these harnesses, not yet. There's some guys in paragliding that are getting close, but even then, they're still sitting up. They've got about a 45-degree angle on their back. So it's, I always like to dig into the correctness of each thing, and to me, it seems more like a seated or a recumbent harness. Supine seems like maybe not the right way to refer to it. So I always kind of throw that in as the first thing to think about. We're going to talk a lot about harnesses, and we're not going to get into the nitty-gritty of designing harnesses or testing skydiving harnesses. But I can tell you that what we're telling you and what we're talking about today isn't we've designed and built stuff that's been jumped, but we've also designed and built stuff that's for sale. And in our paragliding world, we have a line of harnesses. So this is something that we're pretty familiar with. You see the picture there. That's some of the testing. That's actually the reserve loop testing on a harness that our current paragliding harness. Some of the EN testing. EN is a engineering or it's a norms standard society for Europe, and they are basically like a TSO for paragliding equipment. The certification is much like a TSO certification. In some ways, I think it's a little more thorough. In other ways, it's a little less robust. I say that because we'll talk a little bit about what it entails in a second. So you saw the last load test. That's from the reserve loops. So on the harness, this would have a reserve and then the main. And so you have to test strength for both scenarios. So again, it's a little more thorough, right? It doesn't have to take a drop load at 254 pounds and 185 knots, but it has to take a load in a lot of different load cases. So they're static tests. They're not dynamic tests typically. There's about 7 different load combos. It's all derived in the EN norms. EN 1651 is the document. Each static load is held for 5 to 10 seconds, and it's somewhere between 6 and 15 Gs. And it would be Gs because you certify your harness for a set mass. So, for example, our harness was certified for 120 kilograms, I believe, Kev?
Yes.
So we initially ran it for 120 kilograms, and you derive the load, the static loads you take by taking gravity, multiplying it times your mass, right? Mass times gravity is force, or mass times acceleration is force, and gravity is your acceleration. So you get your weight that way. So you end up testing 7 different load cases, and this is one of them being tested. The same specimen has to withstand all these load cases. So you see this one is our main hook-in point load test. And you're not going to see a whole lot. You'll see you're going to start seeing, you can see it moving now. See that the webbing starts to give. You can have little local failures on like fabric and stuff like that, but you don't get to have any failures on webbing. It has to remain structurally intact. The same piece has to remain structurally intact for all of these tests too. So you have to pass all 7 tests, and they kind of get. This is the second test. This is the second. It's pretty easy. If you fail this one, you're kind of starting over. The reserve one was the first one we did. This is the second one, and then you go through them in an order. You see up here. you go through all kinds of different stuff. Like that's a single harness, single riser connection. You still have to pass a load test with a single riser connection. Another one is you have to pass a load test with it pulling down. So like you're inverted and it's pulling. See right there, and some of the fabric gave way there, but it held. Single specimen has to pass all of that. So sorry about that. That's a little more nuanced than just dropping it out of an airplane really fast and you got to do it 3 times, right? These tests, I think that the future holds something a little more in between for some of these things, but I think that there's a lot to be learned from the paragliding side of the house. We get a lot of really valuable knowledge paying attention to the paragliding world. It's hard to do to straddle both industries, but it's paid dividends. They are doing things in materials, engineering, certifications that we're not doing at skydiving, and I really like what they're doing. So I share this with you guys, A, to demonstrate, hey, look, we're not in a vacuum. We know a little bit about harnesses, and B, to also say, hey, look, this is what other industries are doing. As an industry, we should watch that and maybe adopt some of it. It'd be really neat. So why do we like these harnesses? You know, they're fun, but for me, and as being the wing manufacturer, like most of this is aerodynamics, right? And we recognized that early on after flying these with some parachutes as part of our testing to bring them into our original project. Is wow, parachutes fly a lot different. They start flying more like speed wings and they're fast. So we recognized early on that there was an aerodynamic advantage and that we needed to quantify it at some point. I wasn't competing. Kevin wasn't competing. We know a guy that does, though, and he was for a while and kind of wanted to know, like, what's the difference? He wanted to know what he could do and what it was going to be difference-wise for him, and what you could feel what was flying faster, but what position really was the fastest? What position made the most sense? I wanted to truth this stuff with the CFD so that I could model it properly, so that I could say, hey, look, this actually makes sense. And here's where I can predict behaviors now. And the only real way to do that is to instrument the heck out of some parachutes or spend some money and go to a wind tunnel. And so we went in, I think, Sven, was it 2018, 2019, we went to the wind tunnel? Sometime around there. So it's me, Kevin, and Sven, and we all went up to a wind tunnel and spent a couple hours. So besides testing them in flight and stuff like that, like that's really the only other alternative is you can model them or you take them to a wind tunnel. And so that tunnel, incidentally, is no longer in existence. We were some of the last people to be able to get in there, but it's a tunnel that cyclists and downhill skiers use these tunnels pretty routinely to figure out their best aerodynamics. Any Olympic cyclists, actually any Cat A cyclist is probably, or Cat 1 has probably been in a wind tunnel so that they can figure out what their best body position is. Same thing with downhill skiers. They do that as well. So we kind of went there with an open mind and tried to, you know, we thought we knew what we were going to be seeing, but we tried to test everything, and we took Sven and kind of put him through the ringer. We split up our time really and said, hey, Sven, here you go. You get this amount of time and just play with it and see what you see. And the neat thing about this particular tunnel is they ran the speeds, but out in front of you was a drag force and other parameter projected on the floor. So you could sit there and see real time what was changing. It also logged it to an Excel spreadsheet that we kept, and we took a bunch of video as well. So it's neat. We were able to get a lot of different body positions and stuff like that. And Sven was able to play with some of the nuances of what matters for him, because, you know, everybody has a slightly different body. And one of the things we learned talking to the gentleman that operated the wind tunnel is that he sees a lot of the cyclists and the skiers spend a lot of time figuring out little nuanced things that matter for them that are maybe different from their teammates and stuff like that. And so some of this, about half the time in there, Sven was spending with that. And about the other half, we kind of had a test card of okay, these are the body positions we kind of want to look at. And I really wanted to get drag numbers for certain body positions. So you can see there's a bunch of different stuff that we were doing. These are all taken from that exact spot. I just cleaned out some of the backgrounds. So kind of to distill a lot of that down and talk about it is in the order of like the lowest drag to the highest drag. I'm just going to run through the basic body positions. In general, number one was the best body position. Seated, legs tucked up, arm width, arm position like that, elbows, legs together, legs crossed, stuff like that. That varied a little bit, but you could probably make a strong argument that that would be a little bit different person to person. So, but it was pretty obvious that tucked up was the best body position. It's the least drag, best option. A little bit surprising was that this was also a very good drag body position. And I'll say leaning forward with the head above the yoke was a very good drag position. Caught me off guard. I didn't expect it to be so good. I knew it would be pretty good, but it was actually pretty low drag. Seemed to do pretty good. Upright, seated with the legs pulled up, probably pulled up a little bit more than that, but that was kind of third place. And it wasn't super far behind number two. Number 1 and 2 were closer than I thought. 2 and 3 were pretty close. And then we saw a really big jump on number 4. Number 4 is kind of the one that surprises a lot of people, but didn't surprise Kevin or I. And it's that. So leaning really far forward was kind of the worst case scenario. If you run the numbers, as soon as that head dropped below that yoke, leaning forward, drag started shooting up through the roof. And so kind of something that we've been saying for a little while, like that crazy lean has no purpose. And I'm going to go through the rest of it later and tell you the other part that it doesn't do. But aerodynamically, once your head goes below that yoke and exposes that back pad on a traditional harness, all the benefit kind of goes out the window aerodynamically. So that's what the wind tunnel showed us. Pretty neat because we actually have numbers for it. So kind of lock that in with. If you, I just share this stuff so that people can incorporate this in their flying and maybe it helps them. So let's talk about drag of pilot versus the parachute. In general, when you model this stuff and just doing the total drag of it, because we measure once you know your lift and once you know your airspeed, or you don't have to know your airspeed. Once you know your lift and your glide ratio, you can back calculate your drag. I talked about that in my last seminar. Really powerful tool. So I already knew what the total drag for the system was. I had a pretty good idea what the parachute drag was because my model tells me, but my model isn't 100% accurate. It's a model. CFD is good for really good for a lot of things, but at really high angles of attack and at flexible mediums, like with aeroelastics effects, which is what we get a lot of in parachutes, it starts becoming less useful. So I could deduce what my parachute drag was and my body drag was, but it was just a good guess. I had to measure one of them. That's why the wind tunnel was so useful for us, is we measured one. Now I know what's the body drag. So I know the total drag, so I can back calculate what the parachute drag is. You could try to do it the other way, but this was the best way to measure it. So in general, the pilot drag is about 50% of your total drag budget for a system. So half the drag is coming from the person dangling beneath the parachute. So everyone wants to talk about cleaning up parachutes and cleaning things up. My joke for the longest time when I was competing is the best thing you could do for your drag profile would be to chop off your legs. It's also the most inconvenient thing you can do for life, but it's the biggest thing out there in the wind. And that's a good part of why having that seated position is so advantageous. Is you're not hanging your legs down into the wind stream. So that body drag can be half of the entire drag budget of the parachute system. So the body drag is huge. Now, when we were able to go seated to vertical, our drag numbers for the pilot alone were about half what they were when you were standing up. So let's just say if you're vertical, you're creating 100 pounds force of drag. In our testing, sitting down was putting us somewhere in the range of 50 ballpark. That means, you know, if your pilot drag is half the body drag is seated and the pilot drag is 50% of the total drag budget, you can get a 25% reduction in your total drag just by going seated. So it's going to be a pretty good system. So we got the drag. We got the drag reduction. We've all been flying it. Everyone's like, oh, cool, we're going to go super fast. It's going to be super easy. Wait, it's not easy. It actually brought in a ton of problems. And Sven spent 5 years. I've watched him dealing with boost. And we tried everything we could. All kinds of different ideas to deal with boost. Like boost, and when I say boost, I mean coming down, you recover, and then you get an uncontrolled climb. That is a direct effect of reduced drag, guys. That reduced drag is giving us a lot higher speeds. We're reaching top speeds that blow vertical harnesses out of the water now. The numbers I hear from these guys are mind-boggling. Put your mind in a bottle. So we had to design a whole new group of wings. We want to reduce lift in some flight modes. We got to keep lift at low speed because you can't just slam into the ground. And you got to do it all that without adding a bunch of drag at any point. Because if you just want to make it steeper and reduce lift, you add drag, the drag overcomes the additional speed you get and you won't climb. That's a dirty way to do it, but it's not elegant, and it's not going to give you an overall boost in performance. It may increase your top speed. So solving all these problems simultaneously, they're conflicting demands. It gets really tricky, and it's not completely solved, but it took us a bit, and that's a lot of the science behind the HK3 and where we're able to make some cool strides. Is we were able to really reduce lift without adding a ton of drag, and then keep it on the bottom end when we needed it. So it took a while to figure out, but that's the magic of it. Is you have to, you know, every time you encounter stuff new like that, you have to come up with new creative solutions. So let's talk about boost a little bit. What causes it? Think about that for a second. There's going to be some times here in a few minutes I'm going to ask you guys to jump in. So I'll tell you when to take the mute off and hop in. But let's just talk about right now. We're going to make everything simple. Let's assume that everything stays the same on the wing, right? Your angle of attack, your coefficient of lift, your density, and the area of the wing. You're just cruising along at 85 miles an hour, and you're creating 200 pounds of lift. Well, what happens if I go a little bit faster? Let's say I'm going 100. You're going to now, you just added about 80 pounds of lift. Well, if you only weigh 200 pounds and you're producing 276 pounds of lift, what happens? You go up. Go a little bit faster than that. And notice it's a squared function, guys. V squared. Look at that V squared up here in this equation. Another 20 miles an hour faster, you're now creating 400 pounds of force. You're going to really boost. So it's exponential. That's the beauty of the lift equation. So that's why boost is so uncontrollable. Anytime you have a force greater than your weight, you're not in balance. You're going to create an acceleration upwards. You're going to climb. So important piece of information there. I'll have you know, I didn't say anything about drag here, guys. So let's talk about drag and your drag reduction. We've talked about, okay, you're actually getting a drag reduction, right? And how do we use this to our advantage? Well, here's a little graph. This is a fly sight graph pulled out of, I think it's one of Simone's fly sights from when we were testing the HK3, I believe. I don't know if this is on the Mutant or not, but if you look over here, the black line, that is his elevation. You can see right where he starts his turn, somewhere in here. The green line here is the total velocity. And then I've traced on top of it, there's an acceleration phase where you're ramping up. There's a peak speed phase here. And there's a deceleration phase, right? So when we're flying these aircraft, we're gliders. We don't have an engine. But gravity is really our engine. But I want to kind of think about this and give you guys a framework to think about this in terms of airplanes. There's two types of airplanes I'd like you to think about. First would be a sailplane. And if you want to get a sailplane to go faster and perform better, what do? Well, I'll answer that really quick. Is you go ahead and clean it up aerodynamically. Some of the sailplanes have engines on them, but that's just to climb up and they turn it off and glide around. They're going to get really high aspect ratio. They're going to go clear down to the nuances and into surface finishes and clean them up, and they're gonna spend a ton of time reducing drag. If I'm in the Red Bull air races and I want to win, what's the quickest thing I can do to really increase my score? Or I'm performing aerobatics on a high competition level. Kev, you can answer this. What do we do? We want to increase performance on most airplanes.
Put a bigger engine on it, more power.
What are we more like on a parachute? Are we more like a sailplane? Or are we more like an air racer? Your average skydiving parachute has more aerodynamically in common with an air racing machine. So the best way that we can add performance to our wings is to get a bigger engine. So when you're framing on how to take advantage of this drag reduction, think of it in those terms. Like, how can I use this to maximize my engine? Thinking back to when I was competing, it was Jay Maletsky would show up at his swoop meet, and it was a different game. When Jay showed up, the game was a completely different game. You had to get different scores to win. It was just different. And the big difference between Jay and all the other competitors back in the day wasn't that he had better technique in the course, or that he leaned more forward when he was climbing out to go distance, or that he got better water drags. It's that he showed up to the meet with a bigger engine. And it was obvious from the second he snapped onto final that he was coming with a higher airspeed and more power than anybody else. And that was the big difference. There's a lot of other nuances that he was really, really good at. But you want to take the biggest difference that from a competitor that you could see was it, the biggest engine. And there's other guys doing the same thing. Sven shows up with a really big engine. So does Kurt. So does there's quite a few other guys. They're showing up bringing a ton of heat when they snap onto final. I'd argue if you're going to do one thing to help your swooping and to get better swoops, it's going to be bring a bigger engine. So let's talk about how we do that. So all we can do is accelerate, and then at our peak speed, maintain that acceleration. Once you start to decelerate, there's nothing you can do to add speed. There's nothing you can do to change what you already brought, right? You can decelerate slower, but it's already decided at that point. And remember that. Remember what I'm saying here. There's a point in your swoop where you only decelerate. You cannot accelerate. This is true here. We see it right in the graph. You're accelerating, this velocity curve is going up. You've got a peak speed zone, and then it drops off. Where is drag going to be the most important, guys? Hop in. You can unmute and tell me what you guys think. Anyone have an answer? Peak speed, okay. Peak speed's great. Yeah, it is going to have the highest effect on peak speed. Let's look at the time frame that peak speed occurs, though. Look, pretty short, right, guys? So it is very important, and it probably has the highest force. It's going to create the highest drag force, but it may not have the biggest effect on overall performance. Deceleration's pretty short time too. Look at the acceleration part of this curve, guys. That is a long time, and that affects the time you spend in acceleration is going to affect the top peak speed. So acceleration is either a close second or as important as peak speed for keeping your drag reduction down or keeping the drag low. Because a longer acceleration, an acceleration with a less drag is going to produce a higher top speed. So when we look at this curve, just understand that it's not just peak speed, it's not just this, but we don't really need to talk about this a whole lot. I hear a lot of people that like to talk about the deceleration and what they're going to do in their recovery arc and this and that, and I see them leaving a ton on the table up here. On that note, I think that anything other than being a small ball in the harness is probably not a smart use of your drag budget in this range. So sitting up, grabbing your fronts, making a big gingerbread man pose, maybe not the best move. At least that's not what the science tells me. It's not what the aerodynamics tell me. So I want to kind of key this into some things I hear people talk about. I want to do a thought experiment with everyone. Let's just say you're cruising along, you've planed out, you're in level flight, right? And we developed a superpower, which would be an awesome superpower, that I'm allowed to instantly reduce your drag to nothing. I can wipe it out and give you zero drag. That's my superpower. That would be a really good superpower. I wish I had that. What's going to happen? I'm not going to give anybody the answer, but you guys can all pop in and tell me what you think. Say it. Let's talk about it, because I
said, to kind of sum it up again, like you guys have just laid down your swoop, you just recovered, and you're motoring across the grass, and your drag went away. What can you expect to change, if anything?
I wouldn't think anything.
Nothing. Your speed will stay the same, if not increase.
Boost all the way up to exit altitude.
I would say boost as well. Depends on where your drag is, like between the canopy and the body.
Okay.
Yeah. Well, if there's no drag, period, then the only force acting on you at that point would be gravity, right? So you just
for sure
you would initially extend out the acceleration phase until you hit. Actually, like you would technically accelerate for as long as possible because there's no terminal velocity for the canopy or the pilot, right?
Well, hang on.
Okay.
Now I have a question.
So then
this is good. You guys are all thinking. I love this. So
What about the drag on the wing?
Let's pause it now, and let's walk our way through the science on it.
So let me just say something real quick. The drag on the wing, I'll just say real quick. So the drag on the wing, when he's saying the drag is, you've got your forces here. You've got your lift, your gravity, and your drag right now. We can't really add thrust because we don't have a motor. So we just took away all drag. That means your wing. That means everything else to your left. You're left with two forces, which are your lift and your weight. Okay.
All right. So we're going to science our way through this and start with a clean slate. Just like an aircraft, your glide ratio, and I covered this in the last one, is lift over drag, right? And so if I take drag away, I've got no thrust because, again, we don't have a motor. You have two forces acting on you, lift and weight. And at static flight, if you're already level and you're just maintaining level flight and you don't change anything aerodynamically, that is not going to change, right? So let's look at this. There's your lift equation and drag equation and glide ratio equation. So let's look at glide ratio, because basically we can look at this and go, well, I asked what's your trajectory going to be? That's the same way of asking what's your glide ratio going to be? So what happens when you divide by 0? Infinity. So what's an infinite glide ratio look like, guys? It's flat. It's horizontal. That's an infinite glide ratio. So the answer to this question is you'll continue along your level path forever. You won't climb. You won't descend, because you're going to maintain lift equal to your weight, and there's no drag, so you won't decelerate. You won't accelerate because you've passed that acceleration part of your curve. You can only decelerate after your peak speed, guys. So once you've leveled out, you've already established equilibrium. So if I take your drag away, you just continue on. So this is a really powerful thing to think about as we reason our way through how to fly these wings. So I hear people say stuff like, okay, well, I got small and it caused me to boost as I came through my recovery arc. Well, no. Getting small didn't cause you to boost because it just changed your rate of deceleration. You can't accelerate once you're already in your recovery arc. The system as a whole has to continue to decelerate. So the aerodynamic takeaways are that the harness reduces the parasitic drag really effectively. It makes a lot of sense. You maximize that drag reduction at your highest speeds and during acceleration. You want to maximize that top speed to give you more power. That increases the size of your engine, and use that drag to maximize the top speed. You can reduce the rate of deceleration by staying aerodynamic in that phase, but you won't ever actually accelerate in that phase. So let's kind of look at the forces on these wings. And this kind of ties into what we were just talking about, but we really only have a few. There's in flight, it's lift, drag, and weight. Now, we're going to, there's some questions last time and there's some comments afterwards on the aerodynamics seminar. I want to define our local axis in a way that it makes our math super simple. So we're going to say that we all know that the actual force on that parachute is up and back, correct? Because you don't really break it down in the real world. Drag doesn't happen. It happens spread out over a whole wing, and it kind of acts on one net force, and it would be up and back. But for math purposes, we can treat force vectors like triangles. So adding up the lift, the vertical component of the lift, and the horizontal component of drag, they combine out and they add up like a triangle, and you do your vector math, and you can break them down into different components. So when I say lift here, I'm talking about the vertical component of it. When I say drag, I'm talking about the horizontal component of the lift and the drag on the object. The whole system as a whole, because we're going to integrate it because we're a whole aircraft. That's about where drag would act, by the way, guys, just so you know, that somewhere between there and halfway up. So depends on the ratio of the drag of the pilot. If it were exactly even, it'd be mid-span. If you reduce the drag on the pilot, that drag location moves up. And then weight. And weight doesn't change unless you're adding ballast or dropping it. I do want you to look at that. Look at that diagram. And for it to be stable vertically, lift and weight have to equal out. And what do they also have to do? They have to pretty much align, right, guys? Because to make this thing work in the world, you have to be able to add up all your forces. If we're not accelerating in any direction, this is in static flight. You have to add up all your forces and they have to equal 0. And you have to add up all your moments and they have to equal 0. So you can see right there that you end up with a scenario where your effective lift and your effective weight kind of have to align. They're going to move a little bit. They're going to be off a little bit because of the drag, because of that moment contribution, but it's not much. I can tell you, having done the math, it's in less than an inch usually. It's small amounts compared to feet in the length of the lines and the length of the cord. So when we balance that all out, the same stuff that you use to balance statics and equilibrium apply. So I forwarded there to aircraft. When you fly an aircraft, we balance that all out. We have to do that math like that. So that's what an airplane looks like. That's the force diagram on an airplane. Kind of the same thing I just drew there. There's the force diagram on a parachute. So let's talk about the difference. If you look at an airplane, you've got most of your mass is up here. Your center of gravity is right here, right? Your center of lift, that lift into the vertical component resolves somewhere right about here. And that's going to create a scenario where if you don't have a downward thrust on the tail, it generally wants to tip over and go nose down, which is actually a really good thing for an airplane. Not so good for us, but really good for an airplane, because that means that you go into a stall and you get to recover. So you have a stable aircraft. And on the diagram here, you can see they balance out. Most people don't know this. It's kind of a neat little category, a neat little nuance, but most aircraft are producing negative lift on their tail in flight, which is it's that lever arm. It's that moment I was talking about that pries the nose up. It's not a whole lot, because the moment arm of that is pretty long. But the point of all this is that, before you load each airplane up, and before you load it up, you have to check and make sure that you're within stability limits and that you're doing the weight and balance properly so that it's stable and everything lines up. Because if you start moving that CG back here to the very back of this, see where that cursor is, it won't recover from a stall. And if you move it too far forward here, you don't have enough downward thrust on your tail to keep the nose up. So you lose pitch control. Before I go into the next thing, let's talk a little bit about CG on people. Just before I say that, let's just note that none of us do weight and balance on our parachutes before we fly. But on your average person, your weight and balance is somewhere between 50 to 55% of your height. Depends whether you're a girl, whether you have big thighs, you are a chicken-legged gym rat that has a big upper body, or just how you're built, right? It's going to matter a lot. It's going to vary quite a bit person to person. So 50 to 55%, it's usually somewhere in that pelvic area. And on our wings, we actually don't have a way to create a trimming force. The pendulum is kind of what we depend on, as we're underneath that wing. So we've got a little bit of offset that way. But horizontally, we don't have a lot of distance. So if you look here, I'm going to go back real quick. If you look, essentially, because we don't have that thrust, if you didn't have that thrust, your center of gravity would have to be somewhere right underneath your center of lift. So that's kind of where we're at. It's a useful tool and good enough for what we're talking about now to just say the two align. And for all practical intents and purposes, they do. There are some special cases where they don't. I can talk about that in the questions later, but follow me for that they generally align, right? I can tell you for sure that your center of gravity aligns with the V in your risers when you're below your risers. And again, if you look at these photos, you'll see here's a paraglider in a pod harness. His pelvis is probably right about here, and it's located directly beneath the hang point on his risers. So you basically have to have your center of mass aligned with the riser load path. And the riser load path is essentially aligned with the lift location on the wing. Otherwise, you'd have to do a weight and balance on every flight. Think about this for a second, because I hear people talk about CG a lot in harnesses. And that's what I'm getting at. That's what we're trying to talk about here. And
I just wanted to jump in just so that everybody's, again, kind of sum it up and following along with this. What Scott is saying is that when you go jump out of a parachute or even or go fly a paraglider, you don't have to do a weight and balance. And the weight and balance isn't just how much weight there is, right? It's that, are you moving it forward or aft of that center of lift? Because then it becomes unstable and unrecoverable. And so we don't have to do that on a parachute. And so again, this is critical for what Scott's about to kind of move forward with.
Well, we don't do it for us because Kevin and I do it for you.
There you go.
That therein lies one of the biggest problems in design we have to solve, right?
That CG is set in the design.
It is.
Yeah.
And it has to align with the lift and the risers. And here's why. Because so you're using textiles. If we had carbon fiber lines that I could put compression on, maybe I could change these things. But because we're using tension only textiles and tension only materials, you can only pull. And when you pull on 2 points like that, like on the risers, the CG has to line up underneath them, underneath that hinge point at the rings. Again, it's a hinge point. The three ring axis, if I bend below the three ring axis, I can't bend the top of my riser. I can't transmit that twisting force to the top of my riser. So it is a hinge connection for all purposes at your risers to your harness. Does that look like it would work to you guys? Got my CG there and my riser there. It wouldn't work. And that's why we don't see when people lean forward, we don't see that. If you could actually change your center of gravity and move it around underneath the wing, you could do something like this. You actually see something like that. And if you notice, center of gravity, there is a center of gravity on the person. I think that's Sven. And you go up right there. There is the harness connection point, the risers. If you watch swooping, you'll see they align. They have to. So we can't move our center of gravity forward or back. But what we can do, move it up or down. And therein lies the secret to a lot of the fun in these harnesses, is you can actually, you've taken that center of gravity and you've moved it up and basically set it closer to the connection to the risers. The other neat thing about moving it close like that is we've also freed it so that you can move it side to side more. So you can shift your center of gravity side to side. That's the extra harness responsiveness and extra harness sensitivity that you're feeling, because you can now take the center of gravity and move it to the left or to the right of your risers in some cases, maybe outside of that riser connection points. And that's the distance between the up and down and the side to side is what you're feeling for the responsiveness. But I hear it a lot. I hear a lot of people talk about being able to move their center of gravity underneath the wing, front and back. You just can't. You could take it in a hanging harness and test it. And Kevin's got some really good ways of illustrating that in a hanging harness. So
Yeah. So again, just to kind of reiterate, like this is the myth that people talk about, right? You lean back in your harness or you lean forward in your harness and you're changing your angle of attack because you're changing your center of gravity. And that is not true. And like Scott's saying, when he's talking about you can't change your center of gravity, you cannot change it in relation to the wing because you're hanging by a single point. You can change your center of gravity in relation to the riser position, meaning if you lean back more, you might tip. And if you lean forward more, you might tip forward more, but it's just your body, but you're just rotating around those points. If you're not sure
rotate around
that
your center
you
of
trust
mass.
this, if you're not sure you can't trust this, here's an easy experiment you can do to prove this. Go hang in a harness from the ceiling, from ropes or straps, whatever else, whether it be a shoulder harness or a hip harness. Hang in that harness and drop a rope, a plumb line, a plumb bob, right, to either side of you, in line with your risers, right where your risers are, and then go ahead and lean forward in your harness and lean back in your harness, and see if your riser position had moved forward or aft of that plumb bob. Now, if that happens, then that would show that you can shift your weight forward. Or you can shift your weight back and change the angle of attack on your wing. But you will find out that as you shift forward, the only thing that happens is your body falls forward and your body falls back. But the riser itself, if I'm turning it this way, and the plumb bob, they stay aligned. No matter where you do with your body, that stays aligned. So again, this is mostly just to kind of reduce away some myths out there that happen when people talk about leaning forward in their harness and they're lowering their angle of attack or leaning back and that kind of stuff.
So now I'll talk a little bit about this and delve into it. A lot of people will feel when they get smaller or lean back in their recumbent harnesses that they feel like they get a recovery or they accelerate, right? So, and I've talked to several people who feel like that. Let's talk about that. Let's walk our way through that. So we've just said that you can't change your center of gravity. Now, if you change your center of drag locally, your body may swing forward a little bit. If you were a big drag thing and you reduced it, your body may swing forward locally, which means your wing's probably going to swing back a little bit. What's going to happen to the system as a whole? Are you going to accelerate? Nope. As a system as a whole, you're not adding thrust, so you can't accelerate. You may change the orientation of the two and the location of that drag, but you can't accelerate. So, and it's not going to induce an acceleration. If you do anything, you may change the slight pitch of the wing, and that would give you a little bit of higher angle of attack, possibly, but you can't create an acceleration. Anything you do to create an acceleration or a CG change or a perceived CG change is something that's acting aerodynamically. Is my point on all this? Is that if you feel a change in that, you may feel a change, and you may very well feel a change, because what you experience as a pilot dangling beneath the wing, right, dangling beneath on, you've got your wing and you're a mast on the bottom of it. What you feel may actually be different, because if you're recovering like this, you cut drag, you go to here. Well, there's a couple things that happen when you did that. You're going to feel like you're accelerating, right? Because you're moving in relation to the wing, but the wing is probably going to go back, because as a whole, this group can't accelerate anymore. There's no new forces acting on it if it's in level flight. The CG can't be changed, so you're not actually going to weight one riser more and cause it to dive or anything like that. There's a little bit more to that. Some of this, if you're accelerating or decelerating, there are some flight dynamics that can come into play. And a lot of that's side to side inputs, and it gets pretty complicated pretty quick. So today I don't want to talk a lot about the dynamics of it, but I did want to feed that a little bit. And that's a lot of where people's misinterpretation of what they're experiencing versus what the whole parachute is experiencing. Because remember, you may feel like you're accelerating underneath a wing because locally you might be, the pilot might be, but the whole system may not be. And therein lies the danger of taking what you're locally experiencing at the end of a rope on the lines and correlating that to what the whole wing is experiencing. So hop in, Kev.
It can also just be a relative. It could just be a relative experiential thing. And what I mean by that is when you start the recovery arc in your swoop, you're diving and then you start leveling off, you start decelerating at a certain rate, especially if it's a nice continuous arc. It's not a real abrupt arc. You have a nice linear deceleration that's taking place relatively. And if all of a sudden you're decelerating at a certain pace and then you streamline yourself a little more, so you have less drag, then that means the rate that you're decelerating changes. You're still decelerating, but your rate changes. And that to you can feel like you've just accelerated because you've gone from a faster deceleration to a slower deceleration. And it's the same reason why in paragliders, if anybody understands or flies paragliders, we use a vario or a little instrument that beeps and tells us we're going up or down when we're high. And it's because if you're in strong sync, and then all of a sudden you go from strong sync, say 1,000 feet per minute down, to light sync, say 200 feet per minute down, you're still descending. That feels like a positive sensation, which feels like you're all of a sudden ascending, right? But you're still descending. And so it's the same thing in the recovery. Like if you're swooping and you've got lots of drag, you're decelerating at a certain rate. And then at that point, you decide to lean forward. And so now you've reduced your drag a little bit. Sure, you might swing through a little bit, but that's tiny. It's a tiny bit of the picture. What's happening is you're no longer decelerating as fast. And so that sensation can feel as if you're accelerating. That does not happen. You don't accelerate.
So bottom line is we fly these things because way more fun, right? Like, talk about hitting a home run. The paragliders figured out like how to fly a wing. And I think a lot of it's because they spend so much more time flying these things. We may spend 2 to 5 minutes on an average flight, where a paraglider can spend, what's the longest flight you've had, Kev?
6.5 hours.
See? So they spend a lot more time doing it. So sometimes they've picked up on a few things that we haven't. I love it. First time I did it, flying speed wings and paragliders, like, oh my gosh, why aren't we all doing this? And I'm super stoked to see these things making their way out into the world. I'm super stoked to be designing wings to fly with these, and because it's a whole different game and it's fun and it's neat. And it's just awesome. So keep being awesome, guys. And I want to kind of open the floor up for questions a little bit and start talking about that. I am going to try to zoom in here on questions. So, Kev, maybe do you see questions? We might have people ask them verbally because I don't see the chat right now. There we go. Okay. Okay. Well,
there's some on there when you were talking about the reducing to zero drag. Kind of past that. Let's see.
We have any. You guys can just pipe in too if you have any questions. So.
Yeah.
Did we answer all your questions?
And dig up.
Did we say anything? Is there anybody here that heard us talk about something that seems contradictory to what you understand or what you've been taught, and they still either you're not sure that you believe us, or feel like you learned something new? Like, pipe in, tell us more about your thoughts. Sven has a question.
Yeah, I just wanted to. I really love what you guys are explaining and how you're explaining it. We've been trying to get people to understand all of these concepts for a really long time when you're teaching somebody to swoop or like read their fly sight and how to interpret those numbers and go, okay, I went faster because I did this, or I went faster because of this. I love how you guys are tying the pilot and the wing into a system of itself. But I also like the point that Kevin, you made, that people are experiencing this acceleration that they think is happening to them individually from the whole system. So we can see that on a fly site sometimes where the person goes, oh, but I did this and that caused me to go faster, when in reality, it was just that split second of a pendulum effect causing that sort of swing through, right? And I mean, if we're really kind of, talking about how to get serious speed, we want to pendulum through the gates. I'm talking competition wise now, right? So as you're penduluming through, well, that's when your high speeds are. And I love the way that you guys are really explaining that well and educating people. We've had so many camps. We do the Canadian camps, every year. And it's this concept that people don't grasp, that the entire system flies together. There's a little bit of movement, but it's only pendulum affected, not, hey, you're gonna go way faster or further because you did this, essentially. And I love how you guys are explaining that in science terms where people can't really argue it. You know what I mean? You could chat about this all day long and see and go out and practically try things. I mean, Scott knows all the stupid things I've done to try to prove him wrong. It's like, okay, well, I did this, and it is like, no, it doesn't matter. So I love how you guys are putting this together. Kudos.
Thank you.
Awesome. Well, you're a big part of it, Sven. You helped us put some of it together, so thank you. you prominently featured in the photos, so
Appreciate that. Yeah,
it's been fun.
Does anybody here have questions? They understand, like when Scott was talking about the engine, like gravity is your engine. Is there anything there that anybody has any more questions that feel like everybody understands that concept? Okay.
Cool.
Jonas?
I have a couple of questions. First off was do you guys have any plans of introducing like different type of materials for the harnesses for skydiving?
We are not a harness manufacturer.
No. Fair.
So, and we kind of plan on staying that way.
Okay.
Everything we've learned about harnesses, we kind of share. We've shared with in particular one harness manufacturer. We've kind of given them the keys to the kingdom on everything we figured out. And
Okay.
they're working on stuff.
Yep.
But I can tell you, having talked a lot to these guys that are doing it, the TSO process makes so whereas the EN certification for paragliding,
Mhm.
it's more thorough, right? It's a lot of different tests. They're an analog for reality, but they're not reality. But the nice thing about them is there's a lot of different scenarios you're testing, but you can also do it pretty cheaply. So you can try a lot of different things. Turns out a TSO, to do those tests on a TSO, because you've got over 100 jumps on a lot of these systems. The harness portion of them, I couldn't tell you exactly how many they are, and then you get to heavy drops, and heavy drops are really expensive. So it turns out that we're not testing as many scenarios on in a TSO. It's way more expensive. So the idea that you would change a material, which very well could trigger the FAA to require you to do that additional testing, would make it really hard for those guys to justify it.
Okay.
It's a really cash intensive thing, and at this point, there's one company making one of these harnesses, and I'm pretty sure they're not making any money at it yet. It's probably been a negative thing so far, but they're doing all these guys that are doing it are probably doing it to help and grow the sport and see limits pushed.
Sure.
It's nobody's getting rich, right? So that's the balance there is new materials are great, but A, there's a risk every time you try something new. And B, it's expensive.
Yeah.
So that's why we're seeing the advancements in paragliding happen faster, is because the testing is you can run through a cycle of these tests in an afternoon, build one, test it again later that week or the next week. And so
Yeah.
go ahead.
I think say another place you can see some materials being played with are sports that are unregulated, like base jumping. That's a little bit more similar to what we see as far as gear and skydiving. And you can see some of the advancements in some of those industries.
But that was where my question came from, really, is like you see new materials in base jumping and kind of similar type of materials in speed flying and paragliding. And I was wondering if like you guys knew of like if that were gonna be
We don't
somehow
know of anything.
incorporated.
Yeah, we
Okay.
don't know anything specifically, and of course, like Scott said, it's mostly just the TSO is really kind of the big hurdle there to make it happen fast.
Yeah.
So
Everything like out of airplanes is a problem in that rule wise. Yeah. The other question, which kind of started off with the material thing, talking about changing the like the lift of the canopy. I don't know how to formulate this, like, or like articulate this question really, but if we look at the Go Flare wings, they have a different type of riser system with pulleys. We also like seen it before on paragliders with the trim system. Is that like, would that some kind of everybody is smiling. That's awesome. Yeah. Is that the that coming or yeah?
You want to talk about this, Scott?
Yeah, it's coming for sure.
Okay. Perfect.
What it's going to be, it's you don't just take a set of paragliding. Like we have a paragliding wing we're about to release that's got that set up on it, right? We did it a different way. We didn't do it the same aerodynamic way that everybody else did. Everybody else did it with a reflex profile. We went a completely different route, which has been really fun because it produces a dynamic wing that you can do a lot of fun stuff with, but it doesn't fly like a slug when you try and get it rolling and stuff.
Much better handling.
Yeah, we're playing with that, and there's definite real possibilities here. And I think I even sent Sven some stuff that his comment was, "Why do you always send me this stuff a month before the world meet?" So we're working on things. It's a harder problem in skydiving. It is a much harder problem. I've given equipment to some container companies and said, "Hey, look, this is coming. Get ready. We're going to be working with this stuff. We're going to be trying these things." So yes, we are definitely working on it. I can't tell you when. I can't even tell you what it's going to look like, but the long process of figuring that out has been started. And
very nice.
So far, it's very promising what we're seeing. So
okay,
yeah.
So no reason to build my own yet.
I would caution you to not do that. So you can't just take those risers and throw them on any wing. It may not, because the ratio that those risers trim, the trimmable risers, the ratios that they trim to each other, it has to be custom designed to where you've put your lines and how you've set your lines up, and it could cause some wings to just stall when you pull on them. It could cause some wings to maybe possibly become unstable. So
yeah, instability is the other one.
It has to be designed from the beginning as a system.
And Jonas, I'll just say this real quick. Like in paragliding, initially those kite riser systems, that's what they call parakites. That's what they're calling them in the paragliding industry. It's a hybrid between a kiteboarding concept and a paraglider. And the reflex profile, some of you may know what I'm talking about, some of you may not, has been the only profile that companies have been using because it has just the most stable configuration for that system. And the risers also have ratios in trimming as well too that have been tested by the designer to decide that's safe and stable as well. And you know, one company out there in the paragliding industry thought we'll just make a riser so people can put them on all of their wings, and some people put them on normal paragliders, and they found that it doesn't actually equate to the same result. Like you said, stability as far as like stalling, more prone to deflation. Those kinds of things are part of the factor in the equation, and so that all has to be designed and tested. So the profile is part of the process, designing a profile for this system, but also doing the testing to ensure that the ratios are correct so that it can be unstable. And yeah, if you do just try to put it on your own stuff, just know that you're going into test pilot territory, and test pilot territory sounds exciting and it sounds fun, but it's honestly terrifying at times. It can be.
Fair. Thank you for the very good answers. If it's just trying to provoke just a little bit.
Yeah, no, it's good. I mean, we're excited about this stuff. We love talking about it, and I just like to just dig into more about the why. And that's all. So
it's perfect. That was exactly what I was hoping for. Thank you, guys.
Yeah, fun stuff's coming, guys. We got some pretty crazy ideas. We always have, and some of the crazy ideas we had 10 years ago, we're finally starting to like move that direction, and we've got to the point where we feel comfortable starting to do some of these things. So, Sam, I'm reading your question about shorter risers, and I guess I'm not understanding it. If you could hop on and explain your question to us a little bit more, that is something that would be worth talking about. So,
yeah, cheers. Obviously, like the standard standard rise that you get with a unit of 30 inches, but we're seeing a lot more people moving towards the 25-inch risers. Obviously, they're only using them for the hop and pops due to exposure, but people are saying, hey, I'm getting more performance out of them. Is that because not so much that they're shorter and creating a higher center of gravity, but more so because you're bringing the where the toggles are placed, and you're not deforming the wing itself when you're in that that position that you were talking about at the start that had the least amount of drag?
So first I'd say is define more performance, because that's always a little bit nebulous to me when people say higher performance. Are you talking people are saying that they're seeing cleaner recovery arcs, faster recovery arcs, slower recovery arcs, higher top speeds? What are we quantifying here?
I guess it's just people are getting better results, further distance, higher speeds. So this is what I'm getting from those people when they say better performance.
Okay, I can tell you because I've gotten a lot of questions. I got a lot of people calling me early in the year asking what riser length to the V we designed to, so that they could try to alter their existing risers on their system. Now, I'm just going to say it because I know that UPT does not like that. So first thing is, if you're modifying that riser, you really need to talk to your harness manufacturer, because I don't think it's a good idea from that standpoint. Now, just changing the length, there's a couple of things that could happen from changing your riser length. So you're not really going to change. You are going to change where you hang under the wing a little bit when you shorten things up. How do I say this cleanly? It's a very small change, but it does in general. So if you're pitched here and you move up, you've effectively taken the wing and changed the angle it's going to hang out a very little bit. Now, that distance on those risers compared to the overall line length is going to be enough that there's a range that it's not going to be enough to make a big difference in the flight modes. So my best guess is what they're experiencing is a reduction in drag. And sometimes when it's more comfortable, it flies better. You can do things better. It's not about raw performance numbers from a science perspective. It's an ergonomic perspective of being able to reach the controls in a way that gives you the best input. If you're able to control your rears here with short arms versus having to have your arms all the way up or all the way out like that, maybe you can reduce your drag that way. Shortening the lines generally shortens the recovery arc a little bit, makes it a little more pitch sensitive. But again, the amount we're talking about is pretty small overall. So
Yeah, perfect. That's hit the nail on the head. That's what I was getting from this seminar. Thanks.
cool. And then I want to add on that. I want to talk a little bit about that idea that there's so I hear a lot of people are asking, they've inquired us asking about, is the wing going to be deformed if you don't use a certain set of risers, or if they're not connected at the same spot and they V bigger? And so is it going to be deformed in regular flight? No, you're not going to create a deformation. And I can prove that to you. If you're flying FT30 wings, reach up and go up, pull on your front sometime, and then look up at the wing. In general, what you're going to find is the wing doesn't actually deform and stay in the same place it used to. You've just changed the loading on the lines, and your rear lines, depending on how far you go down, your wing's going to stay basically in the same spot. It might reflex a little bit upwards, but not a lot. And in general, your lines are just going to go slack in the rear. So you change the line tension a little bit when you do that, but you don't change the actual the wing. So the idea that being on longer risers or whatever, if it changes the angles from say like that to that, is going to put a pinch in the wing. Usually isn't. At least what we can change on the risers wouldn't be enough. Now you may see some small changes in how the rear risers engage and stuff like that, because you do have a built-in cascade back there that's a triangle, and if you pull the triangle forward, it's gonna activate one line sooner. If you pull it back, it's gonna activate a different line. So you might feel rear riser performance change a little bit. We do notice that, and that is one of the considerations that we make when we're trimming a wing. So we actually have to get that feel right. But the range that people are going to put those risers in where they want the V is by and large not consequential to the overall performance or top speed of the wing. From a design standpoint, there's not something that I'm going, oh wow, that's going to be so much better, or oh wow, that's going to be the worst. Pretty much anything that's being made in the ranges that are out there are probably right near ideal. You have anything to add on that, Kev? You've done a ton of riser work over the years, playing with risers and trimmers and stuff like that. And paragliders, they're a lot more standardized, right? So
yeah, the only thing I would add to that is maybe not so much performance, but handling. When you talk about people changing their riser length, again, it changes maybe that overall center of gravity on the system, so the pilot moves closer to the wing a bit, and so maybe it can change that pendulum a teeny bit, right? And the overall total drag a small amount. When you change harness configurations, we know from shoulders to hips, and then even hips where you have a high hang point versus a low hang point. Now that's going to change your body's center of mass to the connection point. So the closer your body's center of mass gets to the rings, per se, the connection point, the more unstable the system gets. It's easier to weight shift. The farther away you get your center of mass from the bottom of the riser, we should say, your connection point, the more stable that system can get. Overall, there's some other things that can take place as well too, which is the geometry of the harness design. Some of those triangles and stuff like that in the webbing also factor that in as well. But yeah,
that's a great point, Kevin. That's something that I did want to talk a little bit about if it came up. And I see a lot of people, I hear a lot of people talking about wanting to get the rings lower and lower, the connection point to the risers lower and lower. And I'll have you expand on it a little bit. But one of the things I can tell you guys from watching the paragliding world is that in general, that distance between the center of mass and the hang point is getting bigger and bigger across the board. 10 years ago, 15 years ago, it was a much smaller distance, and across the board, for a lot of reasons, we're seeing all the manufacturers go to it. And I'll let you talk a little bit about that, but that is something that I've heard quietly talked about off to the side, and I think that the deeper, bigger distance is actually better for a lot of reasons.
Yeah, so going with a higher hang point, obviously there's some ergonomic stuff that can change that Scott talks about. It makes your risers feel longer to you, right? So the reach can be different. So there's always this balance of trying to move the risers, the top of the risers closer to the pilot for ergonomics and ease of use. But if you come down too low, it can feel like you're balancing on a ball. It can feel like you're balancing on this orange, trying to stabilize yourself. Now, there's some ways you can mitigate that, and that is if your chest strap, you know, if your distance between the base of your risers is wide enough, you can start putting in some webbing that's at angles. You know, some angled webbing that can kind of brace a little bit. So as you start to tip, all of a sudden, let's maybe do this. So all of a sudden, as I start to tip, this engages, you know, to the other side. And so those are some things that you see in paragliding harnesses where there's some triangulation going on to try to stabilize that. And what I mean by that stabilization is two things. Like one, you want kind of a balance, which is you want to be able to feel like, okay, I'm unstable enough that I can just simply lean with very little thought into it. I can lean and I can offset my risers to get that churn that I want, that handling that I want. But what you don't want is you don't want it so low. You don't want the hang points so low, as in close to your hips, so that, you know, you can't create an angle where that force is actually able to kind of stop. So you can lean and then it stops. Because what can happen is if it's really, really low and you don't have that proper angulation going on in the webbing somehow to kind of like catch that lean, it's possible where a person can go into an unstable configuration where they can lean so far that they now essentially kind of fall out of their chair, right? So the whole system, now your center of mass becomes below your hang point. And in that configuration, it can be difficult to upright yourself. Now, in a 1G scenario, you have to get above the hang point. Yeah, above yourself. In a 1G scenario, you'd have to flip almost upside down. But in a high G scenario, 2, 3, 4G scenario, you don't have to get very far below your hang point, your center of gravity, before that becomes unrecoverable, and you're essentially pinned into a weight shift scenario that you can't upright yourself from. So that's where the balances take place. And we found that the higher you get the hang points, the safer that becomes. The passive stability is that it's more difficult for you to get your center of mass so far over the top that you can't upright it. Yeah, you're saying that the center of gravity below the hang point. You don't want to get the hang point below that point. So, did I explain that well? Maybe
yeah, that was good. It's so the trend in paragliding on most available products, even in the acro world, they've gone a little bit higher on the hang points. So when I hear skydivers say they want to move down, it's kind of like, let's think about that and move the other direction a little bit. It'd be good.
And one thing I'll add to that is, you know, this is not as much a scenario in skydiving because generally people, you know, buy a harness that's sized to them, fitted to them, so forth. Unless you're buying used gear, you can buy something small. And really, we only see this in the hip harness world. So in paragliding, if any of you guys who are getting into paragliding are into paragliding or speed flying, and you go buy a harness that's very small for you, too small. There's also some other stability quirks that happen with the yoke coming over the shoulder and that angle to the carabiner. So that the higher that angle is, the more stability you have again there, where you can weight shift easily, but you're not likely to get flipped inverted and be stuck that way in a high G scenario. And so if you're wearing a harness that's too small for you, you could potentially bend over backwards in a high G scenario and get pinned to where you can't, again, bring yourself upright. So for those of you that are in speed flying, paragliding, whatever else, it's really important that you are flying, one, a well-designed harness, but two, it's properly fitted. You're not wearing something too small.
Exactly. So if you're getting that gear, get with somebody who sells these things and spend some time in a hanging harness and get fitted, because it does matter. So good deal.
Is there anything else, folks? Because we love to hear ourselves talk.
Well, good deal. We're at about an hour and a half, and I think the questions have dried up here. So I think it's probably a good time for everyone to go enjoy a frosty cold beverage if that's in your time zone. And if not, go back to work.
I'm going to go back to work.
But thanks guys for checking in with us. We're going to do more of these. These are not going to be one and done type things. Let us know what you want to know about next, because we only have one or two more of these that are canned and ready. So we need feedback on what do you want us to talk about? What do you want to know about? What can we share with you that that we've been able to pick up over years of doing this and pass along. So thank you. And I appreciate y'all.
Thanks, guys.